Is the screen visible?
Yes, it is.
Okay. So I believe this is week 8 of the course. So we'll just start with a brief recap for you and those who are watching on YouTube, and then we'll solve some questions. So recap. So what we saw last time was that angular momentum is composed of two things. One is due to translation of center of mass when it is not moving along the line that is passing through the origin of your coordinate system, and plus an intrinsic angular momentum that does not depend on where your reference frame is. This is purely due to rotation, right? And then we saw that m is in general not proportional to the angular velocity, right? In fact, mi is given by iik times omega k. So there is a matrix relation between them. So vector m is some matrix I times omega, right? So this is your moment of inertia tensor, and the form of I is given by this thing. On diagonal you have sum of squares, so this at x you would have y square plus z square, and here we would have x square plus z square, and at this place you have x square plus y square, and off diagonal terms are mass times, if it is y then x y, right? This is xy component, then xz component would be xz, right? And this would be minus yz, and it's symmetric, so this is equal to this one is equal to this, and this thing is same as this one, right? So clearly it's not diagonal, but we can make it diagonal. So when you diagonalize it, we have tensor that has only I1, I2 and I3, right? The eigen values and the eigen directions or eigen vectors would be your principal axis. Okay, so note that it is principal PL, which means main axis. Okay, so properties of I. One is that I is positive semi-definite, right? We used this notation earlier, which means that all eigenvalues I1, I2 and I3, all of them are positive or 0, right? And then Mi is in this coordinate axis, in principal axis, your Mi would be just Iij times omega j, right? And this can be written as delta Ik, right? And then Iij times omega j. Is that correct? No, this will be just Ik because we are summing over k, right? So this at the end becomes just Mi omega I or Mj omega j, whatever you want to call it, right? So Then we have three cases or three tops. Anything which is rotating, which we just call it a top. So the first is perfectly spherical symmetric top. It means orientation doesn't matter. You look it from any angle, it looks the same, right? A sphere basically. So for that you have I1 is equal to I2 is equal to I3. Okay, and then your M is I1, or you can call this I. So it becomes I omega 1, I omega 2, and I omega 3, right? So it is just I times omega. So for a spherical symmetric top, your M is always uh, in the same direction parallel to your omega, like what we studied in 12th standard. The second is remove some symmetry, so axially symmetry or really symmetry. That is symmetry about only one axis. In that case, two of them would be same and the third one would be different, not equal to I1. Okay, so in that case, you can say that there is this axis which is symmetry axis. So one of the principal axis is your symmetry axis and other two are the perpendicular to it. Okay, and you can take any two directions which are perpendicular to I3 because it's actually symmetric. And the third one is nothing, no symmetric, general case, which is without any symmetry. The term we used was asymmetric top, in which I1, I2, I3 all are unequal. So these two are different, these two are different, and these two are also different. Okay, so in this case, you can't make any statement about where the principal axis would be because there are no symmetries. You just have to do calculations, diagonalize your matrix, and see. Okay, so after that, we calculated the Lagrangian, so kinetic energy, right, which is half mv square. And for v, small v, which is in your body frame, can be written as capital V, which is the center of mass velocity plus velocity due to rotation, right? And when you put this at the end, you get something like half mu v square plus half omega j I j omega L. Okay, so how do you read this kind of equation? So first of all, we have used that it's in center of mass frame. Okay, so that this sum m times r is equal to 0, right? So the first term is energy coming from the center of mass, okay, the translation energy, and this second term is due to rotation. So you can see if I is diagonal, then we can write, if it is diagonal, then we can write this as sum of omega 1 square I1 omega 1 square plus half I2 omega 2 square plus half I3 omega 3 square, right? So we often make analogy between translation and rotation. So in translation you have half mv square, and if you write component wise, then if you would have half mv1 square or vx square plus half m vy square plus half m vz square. So omega 1, omega 2, and omega 3 work as your Vx, Vy, Vz, these are angular velocities, these are linear velocities. But an important difference is that in this you have mass terms same, the coefficients, while here they could be different. Okay, so that is important to remember. This is where analogy breaks, kind of. Okay, then we looked at rocks in space, and we saw one particular thing, that for axially symmetric rock, you can have precision. So suppose your principal axis is this. Okay, so you have a top that is something like this. So you have x3 is one of your principal axis, and you can have x1 along this and x2 coming out like this. Then you can have angular momentum in any direction, and in that case your principal axis, this axis of symmetry, would rotate around it. So the entire object would rotate about one of its principal axis, this symmetry axis, and this axis itself would rotate about this. Okay, so this is called precising or precision motion. Okay, and then we show that rotation speed of precision, omega pr, is simply m divided by I1. Okay, so that was something that we saw. And the last topic that we saw was omega in terms of Euler angles, which we had seen last week or last to last week, right? So what we had done was, if you had x, y, and z, first you rotate x such that you come to the plane of the nodal line, that is the intersection line between xy plane, the old xy plane and the new xy plane, right? This angle we called phi, and then you rotate about this nodal line by some angle which we call theta, so that your z prime is set up. Okay, and then you rotate about z prime so that you get to correct x prime, and in doing so we get the correct y prime as well, because they have to be perpendicular following the right-hand thumb rule. Okay, so this angle which we called psi. So if you see, we rotated phi this way, which means the direction of phi dot would be in this direction, right? Similarly, psi was rotated this way about z prime. So psi dot would be in this direction, and theta was rotated about which one? Sorry, this was theta dot, because we rotated theta this way. And phi was rotated along z. So this was phi dot. Okay. So after that we can write theta 1 dot in terms of psi and theta and pi, right? So we can do entire thing, and then finally we got omega 1 as pi dot sine theta sine psi plus theta dot cos psi, omega 2 is pi dot sine theta cos psi minus theta dot sine psi, right? And omega 3 is pi dot cos theta plus psi dot. Okay, and one thing which you can notice is that omega 1 square plus omega 2 square plus omega 3 square, this would be your kinetic energy, right? Rather half I1, half I2, half I3, right? And this in general is not proportional to theta dot square plus phi dot square plus psi dot square, right? There are in fact plus cross terms. So when the top is symmetric, that is when I1 and I2 are equal, you can explicitly calculate omega 1 dot, omega 2 dot, omega 3 dot, and you will see that the cross terms are of the form 2 theta dot psi dot cos theta. Okay, so and then in the end we calculated Lagrangian for heavy symmetric top. Heavy symmetric top, that was half I1 prime phi dot square sine square theta plus theta dot square, right, plus half I3 phi dot square cos square phi that cos theta plus I dot whole square. So there won't be square here, and minus mu gl cos theta. In proving that, we use two theorems. One is that if you shift your origin to center of mass, and if you use vector A for that shifting, then your I prime KL is IKL plus mu times delta KL A square minus AKL, right? So for K is equal to L, the shift would be the components along KL axis of AK, right? So that's what we did this week. Now let's solve some problems. Does anyone have any question in this discussion? Okay, then let's proceed. So questions are again as usual simple. So the first one is that IKM denotes the inertia tensor of a rigid body. Then the following second ring tensor, this one, evaluates to what? Okay, so the given tensor is epsilon ijk, epsilon ilm, epsilon jk. First of all, we should identify the free indices. So I is not free because it is being summed over. J is also repeating, K is also repeating. So only L and M are free. So whatever this tensor is, it has two indices for second rank tensor. Right. So this is some TLM. Okay. Another thing that we notice is that this JK and this JK are similar, but one of the pairs appear in this symmetric tensor, right? Inertia tensor is symmetric, and this is anti-symmetric. So we can change J and K. So I can write IKJ epsilon ILM epsilon kj, right? What I was calling J is now being called K, and what was K is being called J. This we can do because both of them are dummy variable. We can rename them to anything, right? You can rename it to A, B, C, D. So why not K and J? So this is just a rename, right? Now we use properties of symmetry. This is anti-symmetric, which means if you change two components, switch the positions of two components, you get a negative sign. So epsilon kj would be negative of epsilon ij. Right? We are fixing I and switching these two. So I get negative sign. This is epsilon ilm and this is epsilon. And again, I switch these two positions, but that doesn't give any negative sign because it is symmetric, right? So epsilon is anti-symmetric and I is symmetric, okay, under the interchange of two variables. Now if you look at this, it's same as the what we started with, except that there is a negative sign. So this is in fact minus TLM, so which means 2 TLM is 0, which means TLM is 0, which means all the components, any LM component is 0. So the tensor itself is equal to 0, right? And you can directly see it because you have multiplication of one anti-symmetric tensor and one symmetric tensor, right? And then you are adding them. So you are taking the trace along those two axes. So it's called partial tracing. If you do quantum information or something, this will be very useful. Okay, so did everyone understand this? Okay. Second one is imagine a rock that is symmetric but not spherical. So only one axis of symmetric top. It's thrown deep in space away from any sources of force. So now it's free. Then observe that inertial frame of reference which its center of mass is at rest, and a student claims that as the rock is symmetric in the shape, there are no forces on it, so the rock can only spin and there cannot be any precision. Is the student's claim correct or not? So can someone answer that based on the discussion? Just simple yes or no. Anyone who is present? Sumit?
Yeah. Am I audible?
Yeah.
Okay, I was trying to. Okay. I think the answer should be no.
Okay.
There would be a precision. We saw
Okay.
that in the lecture, right?
Yeah, exactly.
Yeah.
So we saw that in lecture if you have a top, and in fact we saw that in childhood. If the top is not exactly perpendicular, you see, right? It precedes around its axis, right? And another example would be that of Earth. Earth has its axis of rotation, and that itself is precising. And although that time period is very large, some thousands of years or millions of years, something, right? So there can be a precision when the top is symmetric. Okay, and one question. Okay, next one is in asymmetric top, the direction of its angular velocity omega points in the direction of intrinsic angular momentum m only if m is parallel to one of its principal axes. Is this a correct statement or not? Okay, so it's given that it's asymmetric, right? So now you have m, and in it also has some principal axis, right? So in that axis you have I1 omega 1 plus I2 omega 2 plus I3 omega 3. The question is, can this be parallel to omega? And the answer is only if omega, yeah. So for that, so if something is parallel to, if vector v is parallel to omega, right, then it means we should have v0 omega 1 plus same v0 omega 2 plus same v0 omega 3, right? Then only we can write v0 times omega, and then it would be a parallel vector. Okay, so in our case, the omega 1, I1, I2 and I3 are unequal. So so clearly these v zeros are different, and then you cannot take it out common, and then there cannot be, uh, so m cannot be proportional to omega unless two of them are zero. So let's say omega 2 is equal to 0 and omega 3 is equal to 0, right? In this case, So I should write omega 2 and omega 3 magnitude. In this case, m is just I1 omega 1, right? And then m is parallel to omega. Okay, because in the other directions it's not spinning, therefore the angular momentum is parallel to omega, which is in the same direction in which it's spinning. Okay, so this is in fact correct. It's parallel, m is parallel to one of its principal axis. Only then you can have omega pointing in the direction of m. Okay, good. And then so these were the only questions from the assignment. So then I have some two extra questions that we can do. So the basically calculate I1, I2, I3 for diatomic molecule. Okay, I'm giving this question because it's not there in assignment, so it's a good idea to have some basic calculations in what we are doing. So diatomic molecule meaning one has m1 mass, it is distance L away, and there is m2, right? And we want to calculate I1, I2 and I3. So clearly the center of mass would be somewhere between them. If they are equal, then it would be exactly halfway. If m1 is heavier, then it would be towards m1, right? So the principal axis, you can think one is this way, right? It's a symmetric top. So this is one axis, let's call it x1, and other two would be perpendicular to that. So x2 and x3. Okay. So let's calculate first of all the position of center of mass. So let's say this is x is equal to 0 and this is x is equal to L. Then xcm would be m1 times x1 plus m2 times x2, right? Upon m1 plus m2. So x1 is 0, right? And x2 is L. So first term is 0, the second is m2 times L divided by m1 plus m2. This is standard stuff we did even in our school. Okay. So this is the position of center of mass. So now let's calculate I2. So for I2, we need for mass 1, it's sum of mass times distance square, right? Distance from that axis. So for the first mass, we have m1 and the distance from this line x2, which is just xcm square. And for the second one, we have m2 times this distance. So this distance would be L minus xcm square. Okay. So this is m1, xcm is m2 square upon m1 plus m2 whole square, right? And L square plus m2, and L minus xcm would be the same thing, but instead of 2 you will have m1. So it is m1 square divided by m1 plus m2 whole square L square. Now you can take out m1 m2 common, okay, and L square. So what you will be left with is m1 plus m2 whole square. So in this you get m2 and this you will get m1, which gets cancelled with this one. So you get m1 m2 by m1 plus m2 L square. Okay. And if you remember, this is your reduced mass. So mr L square. And this is what we did in planetary motions as well. When you had a sun and earth, you said that instead of that we'll go to coordinate system in which the origin is some fixed thing, and there is a mass, a reduced mass, which we called mu. But in this context, we generally use mass mu for total mass. Okay, so I'm calling mr. So in this case, mu would be at some distance L, right? So we are using, or rather we called it r, small r. Yeah, so it's the same thing. Okay, once you know I2, we know that I2 and I1 are arbitrary, right? Perpendicular to this. So this is I1, this is I2. So both of them should be same because x1 and x2 should be same. So I1 is equal to I2. And what about I3? So I3 is x3 is passing through this point. So the distances of the mass from the x-axis would be 0. So I3 is 0. Okay. Okay, good. Now we can do a slightly more involved calculation, that is of triatomic molecule, but not like one which we saw in earlier weeks, rather in a plane. Okay. So we have 3 atoms, but we impose some symmetry. One is that the triangle is isosceles. So this distance is, let's say, some b, and this distance are a, and these two masses are equal, m2 m2, and this is m1. Okay, and we want to calculate the principal axis and angular momentum, sorry, the components of I. So obviously it also has got symmetry about this axis. Let's call it x3. Okay, and the center of mass would be on this line. So you have two masses here, one here, so it should be somewhere around here, right? Okay, so this is your center of mass, and perpendicular to x3 axis you have one axis that is inside the plane of this triangle or the plane of the screen. Let's call it x1, and let's call this one x2. Okay, so let's calculate I1. For I1, first we need the position of center of mass. So let's say this is some distance d, then d would be m1 times this height, right? So let's say this height is h, that we can calculate in terms of a and b. So it would be a square minus b square by 4, right? Because this is b by 2. So then d would be m1 divided by 2 m2 plus m1 times h, right? So I1 would be m2. Let's say we are calculating for this one. So for that, m2 is d distance away from the axis. So m2 d square. Same thing again for this one. It's d distance away. So m2 d square and plus m1 h minus d square. Right. So 2 m2 d square. D square is we calculated in terms of h. It's m1 by 2 m2 plus m1 whole square h square plus m1, and now for h minus d, uh, so this is d. So when you do h minus d, this numerator denominator becomes the numerator minus m1. So 2 m2 divided by 2 m2 plus m1 h. So this becomes 2 m2 divided by 2 m2 plus m1 square h square. Again you can take something common. So you have 2 m2 m1 is common. The denominator is 2 m2 plus m1 whole square. This h square is also taken common. So now what we are left with is 1 m1 and 1 2 m2. right? And that is exactly this denominator, so it gets cancelled, and you have 2 m1 m2 h square. Okay, good. Now second axis, which one should we calculate? Let's do I3 first. So for I3, m1 is passing through I3, right? This is your I3 axis. So m1 is passing through it, and this m2 and this m2 are distance b by 2 away. Okay, so I3 becomes, for m3 it's 0 square, sorry, for m1, is it m1? Yeah, this m1 is 0 distance away, and m2 is b by 2 distance away, and the second m2 is also b by 2 distance away from I3. So it becomes m2 b square by 2. Okay, that is your I3. And I1 also we can, I2, sorry, the distance, the inertia along this axis can also be calculated using this thing, but we can use one important result or theorem, which is that it's equal to I1 plus I3. And why is it so? So the theorem is that whenever you have a planar object, and if you have this as Ix and this as Iy, then your Iz would be sum of Ix plus Iy, right? And if you stare at it, if you think about it, it becomes immediately clear. So in this, you are calculating square of distance from some general point, right? And that is equal to distance along this x-axis plus y-axis. So x square plus y square becomes z square. Okay, so from Pythagoras theorem, this is only true for a planar object. So you can just plug it, m2b square by 2 plus whatever we got, 2m1 m2 h square. Okay, so I just wanted to show how to do these calculations, how to use these kinds of theorems, etc. Okay, so that's all I had from my side. I'm sure if you have any questions, you will ask me. Raku, Elizabeth, do you have any questions?
No.
Okay, okay, if not, then we'll meet again next week, same time. Okay, okay, bye everyone. Happy learning.